Ladies and gentlemen, this class recording has started. So, last week we started getting into our unit dealing with Newton's laws and forces, and we said that forces answer that question of why for us. Why do all these things happen? Earlier in the unit earlier in the previous unit, when we talked about kinematics, we talked about what's happening, where is it happening, when is it happening, but we've neglected to tell us the why. That's what this unit's about. And then we talked about Newton's first law. Newton's first law gets summarized in one word, right? What is the one word? Inertia deals with Newton's first law, not oh crap. That's two words, by the way. So, all right, inertia, right? Whatever something is currently doing, it's going to keep doing, right? Or Newton's first law deals with things staying the same. But then Newton's second law deals with what? That's one part of it, but more important, Newton's second law deals with acceleration, or deals with things changing. And there are two factors that affect the acceleration of an object, right? Net force and mass, right? And we put them together in this equation, right? A is equal to F over m. We talk about the mathematical relationships that exist, although usually you'll see it written in this form. Okay? All right, good there? So on Friday, we got into the idea of, oh man, oh, that's right. What? They go to the library? What? Oh, maybe they have a lot of people that are missing for the leadership retreat. So, you know. Yeah, they left yesterday and they come back today. So. They get like nominated by teachers, basically. So. They can. You can decide whether you want to go or not. So. Sorry, happens sometimes. All right, don't say anything bad about your mom. You're being recorded, so you just be careful.
I love you, Mom.
All right, so on Friday, and I apologize for this because when I was closing down my computer on Friday, I went to go close my file. This is like my file that has all the stuff we did in class, and it said, do you want to save changes? And I accidentally clicked no, so all the work that we did on Friday is all gone. But anyway, we talked about that net force, right? Net force is represented as the sigma f, right, where the sigma means a summation function, meaning we're adding all the forces together, which is fine when we have Larry, Moe, and Curly pushing this boat. We either add forces if they're in the same direction, subtract forces if in their opposite direction, but when we move into two dimensions, right, now that sigma, right, requires that we take the vector sum. These two forces here, right, we have one force this way, and we have one force this way. We said that in order to find the vector sum, right, we're going to basically make a triangle out of these forces as much as we can. Here, even though they are set up in a way that we could technically make a triangle like this, right, we said that what we really want to do is line them up so that one starts where the previous one ends. So instead of drawing our forces that way, right, we can set up our second force to go like that, and then our vector sum, or our resultant vector, is the hypotenuse of that triangle. Okay? That being said, let's take a look at something different. If you would please, open your book to page 182. 182. Oh, crud. All right. So, this problem is on page 182 of your book here, and it says, to give the 19-kilogram child a ride, two teenagers pull a 3.7-kilogram sled with ropes, as indicated in the figure below. Both teenagers pull with a force of 55 newtons at an angle of 35 degrees relative to the forward direction, which is the direction of motion. So they give you a picture, kind of shows how it's all set up. Okay? In addition, The snow exerts a retarding force on the sled that points in the opposite direction of the motion, has a magnitude of 57 newtons. Find the acceleration of the sled and the child. So, let's go through this, right? First things first. All right, that's our unknown, yes? Okay. For the sake of time, I'm just going to kind of go through this a little faster so we get through this and make sure we get it done. Okay. All right, so 19 kilogram child, 3.7 kilogram sled. They're both moving, so we'll go with our mass of 22.7 kilograms. Okay? Did I do that math right? Yeah. Just add them together, right? Because they're both moving, so we'll just add them all together, and we'll consider them to be one object. Because the sled can't move at a different acceleration than the child would. That wouldn't work, or at least not for the child. So, all right, and then it tells us about three forces. So let's start off with which color? I'll use this pink one, right? All right, I'm going to start with this one. Snow exerts a retarding force on the sled, opposite direction, magnitude of 57 newtons, right? So, force of the snow is 57 newtons. All right? I realize that I haven't given you a vector part yet, but we'll save that for a second. Or we'll save that for a little bit, okay? Then, there are two teenagers, right? We'll call this one here force 1, force of teenager 1. It's 55 newtons, but it also gives us this angle of 35 degrees, right, as shown here in the picture. All right? Then we'll take this one, and we'll call this one force 2, also 55 newtons, also at an angle of 35 degrees, but in a little bit different orientation as we can see in the picture. This is where the picture would be important to go along with this problem. Trying to describe the differences between all these forces might be difficult without a picture. You could do it, but it might be more difficult. That's why the picture together will be good here. Okay? All right. So we know if we're finding acceleration, right, there has to be what acting on the kid in the sled? What causes this acceleration? Net force, right? So there has to be a net force. We know that the acceleration depends on two things, net force being one of them, mass being the other one. We got the mass, now we got to find the net force of these three, okay? Because they are not all in one dimension, we can't just add them up, right? We have to find the vector sum, which there's a couple ways you can do it. Here's how I would suggest you do it. Now, in this case here, we got, wrong color. There we are. We have, this is the force of the snow, right? Then we got force 1 pulling this way, and then force 2 pulling this way. All right. These two forces, force 1 and force 2, they are not perpendicular to each other, right? 35 and 35 doesn't add up to 90. So we can't use Pythagorean theorem to find the vector sum of these two, right? It just doesn't work that way. It's not right triangle. So here's what we do. In this case here, we have two forces that, sorry, let's back up a little bit. When we were in one dimension, what was our frame of reference? What was our coordinate system? What did it look like? There was a 0, but then what else was there? We were in one dimension. How many choices did we have? 2, this way or that way, right? So our frame of reference or our coordinate system looked like a number line, right? We had a 0 point, we had a positive direction, we had a negative direction, right? Similar to this track and the motion detector, which we'll use again tomorrow, okay? But these two, F1 and F2, are not on that line. F of snow seems to be on a line, but 1 and 2 aren't, okay? So we have to transition into 2 dimensions. In 2 dimensions, we need to account for our x forces, but also are y forces. So our coordinate system now can change from a number line to two number lines. But when we put two number lines together, right, we basically make an xy axis, right? That's what an xy axis is. It's just two number lines, one horizontal, one vertical, right? Okay? So when we move into two dimensions, our coordinate system changes to look more like an xy axis. Now, what does that do for us? Well, what do we know about the x-axis and the y-axis in relation to each other? What's the angle between the x-axis and the y-axis? 90 degrees, right? They're perpendicular. So if we can somehow get this force onto one of these dotted lines, now we can just add everything up. As long as we have a bunch of forces on a dotted line, now we can add them, subtract them, just like we do in one dimension. Does that make sense? Okay. So, F1 is pulling up into the left, right, in this diagonal direction. But as we discussed earlier, right, there's actually two parts to this force. If we have a force that's pulling diagonally up and to the left, there is a part of it that is pulling to the left. Oh. And part of it that is pulling up. Make sense? Okay. Do you remember what we called those two? Gave them a name the other day. Anybody remember? The specific vectors. They are the component vectors. Okay? And F2 is pulling diagonally down and to the left, which means it has components as well. It has a component to the left, and it has a component down. Okay? Good there? Now, I didn't connect everything, but what have we made ourselves now? Two right triangles, right? And we know something about those right triangles, yes? What do we know about each of those right triangles? They're the same. Technically, they're not quite the same. One's going up and one's going down. They're similar. How about identifying parts of this right triangle? What parts of this right triangle do we know? We do know all three angles, right? So we know that this is 35, right? And that means, well, if this is along this way and this is along this way, that means that that has to be a right angle, okay, which it is. And then that means we could also figure out what this angle is right there, right? Be 55, okay? So we know angles. What else do we know? Which side specifically? We know the hypotenuse of this triangle, right? This hypotenuse is 55 newtons. Goodness gracious. Apparently the board is rebelling against Monday. Okay? That being said, we can figure out the two sides of that triangle, right? And like Cindy said, if we do it for one triangle, we basically have done it for the other triangle, right? So let's take a look at this component of red, the horizontal component, right? As far as abbreviation goes, right, we could call it F1 of x, okay? Just using our subscripts to further, make sure we understand what side we're talking about here. So this would be F1 of x, all right? In relation to the angle that we were given in the problem, what side of the triangle is that? It's the adjacent side of the triangle. We also know, which is what part of the triangle? The hypotenuse of the triangle. So if we know the adjacent and we know the hypotenuse, which trig function can we use? Cosine, all right? So in this case here, cosine of not 55, cosine of 35 will equal the x component over 55 newtons. Does that make sense, where I'm going with this? Yes, no, maybe? Yes, put it back in degrees. Yeah, I know it's going to be a sucky thing all year long. I'll try to remember to tell you, but it's probably a good idea to ask too. If I forget, you can ask. So, and then that means we can also figure out F1 of y, or the y component of that force, by using which trig function? We could probably use sine, right? We technically could use tangent because we would know this side, but if we use sine, right? So sine of 35 would then equal F1y over 55. Right? Does everyone get the F1y notation? We okay with that? What that's telling us? Okay. So, Evan, do you get the idea that this force, this 55, has some part going horizontal and some part going vertical? Okay. We refer to those as the component vectors of this force, the horizontal component and the vertical component as they're drawn on this picture. Does that make sense? So we use the x and the y to represent horizontal and vertical because on an xy axis, usually the x-axis is horizontal and the y-axis is vertical. Yep. So that would be F1 of x would be this side right here. F1 of y would be that side there. And then that would make this side here F2 of y. And then this side would be F2 of x. Does that make sense? All right. Everybody find these because I didn't do them yet. Anybody actually have their calculator out to like? What is it? 45.1. Oh. And what's this one? 31.5. Okay. And then that also means that F2 of x is 45.1 and F2 of y is also 31.5 because, Cindy, we said those two, what do we know about those two triangles? They're similar, but there is one thing that makes them different, right? So now, ultimately we are doing this because what did we say we had to find out to solve this problem? The net force, right? We already know the mass, but we got to find the net force. So we need to find the vector sum of all this action going on here. Say again? It's 0, Devin, on which axis? The y-axis, right? What we do when we find the vector sum of all these forces, once we split them up into their components, now everything is either on the x-axis or on the y-axis, right? And if we have forces that are all on the x-axis, that's one dimension. And if we have forces that are on the y-axis, that's one dimension, right? Remember back in when we did projectile motion, what do we know about the x and y axis? What was the big key to solving projectile motion problems? What do we know about the x and the y axis? It could be. I was thinking something different. X and y axis. No, now we're just throwing out words. Frame of reference, vector sum. The x and y axis occur simultaneously, but they are independent of one another. Right? Sound familiar? Yes? Okay.
Yeah.
So that means we can analyze the x-axis separately from the y-axis, right? Cindy, these two triangles are the same, are similar, but they are not the same, right? The one big difference, and Devin noticed, right, is, Devin, what's the difference between the two triangles? One's positive and one's negative on which axis? The y-axis. So technically, on the y-axis, this component is positive, but this component is negative on the y-axis, right? Does that make sense? Okay. So on the y, are there any other forces on the y-axis in this problem? No. So, Devin, we kind of noticed, right? What happens when we add these two y-axis components together? We get 0. And those two cancel each other out. Great. Okay? Now we're left with the x-axis. How many forces are there on the x-axis in this picture? 3. Right?
Oh, it's all on net
Now we got to do net, right? Because net means to sum them all together, right? On the x-axis, we have, let me do this. See if this works. Probably not, but we have this one, we have this one, but we also have this one, right? So we have to find the sum of those 3. What do we see about 2 of them? They point which way? They're the same, but they both point to the left, right? What about this one, though? What about this? What about the snow force? It points to the right. So when we figure out the sum of all those, right, we're going to add these 2, but subtract that one. Yes? Okay, very good. Nope. We keep kilograms as our base unit for mass. Remember that newtons is a kilograms times meters over seconds squared, right? Okay. All right, so that means that our net force on the x-axis, right, sigma Fx, is 45.1. Actually, I should do this for color consistency. I will try to remember. I am recording it, so. Okay. So, positive 45.1 plus positive 45.1 plus negative 57. Right? Those are our 3 x-axis forces. Put them all together. I realize this is a huge mess, but what is it? And because the y-axis components canceled, that's our net force. Now we know the net force. Now we know the mass. We can find the acceleration. It's probably going to be somewhere about 1.5-ish, 1.46. Yeah.
Acceleration force over mass.
Yep. F equals ma, or A equals F over m. Okay. All right, good there? Okay. So for tonight, these problems that are on the calendar here, okay, these all deal with, these all deal with forces in 2 dimensions that we have to split up into vector sum or component vectors, and then add the x-axis components and the y-axis components, right? Answers are not posted yet. I will make sure that those get posted so that you can check those out and see how we're doing, okay? What's the unit for acceleration? Come on, we should know this by now. Meters per second squared. All right, tomorrow we'll be on lab looking at the relationship between force, mass, and acceleration. So we'll do Newton 2 lab tomorrow. Quiz Wednesday night for take home.